Hello friends! Welcome to Incredible Innovations. In this video, we will show a new breed of robots. German electrical company Festo has pushed the envelope in these kinds of robots. They are trying to make robots, which are inspired by Mother Nature. So stay tuned, and please subscribe to our channel. They are very important for our motivation. Bionic Handling Assistant. Elephant's trunk is a very complex and most versatile tool, used for breathing, smelling, touching, grasping, and producing sound. It's probably the most amazing body part of the animal kingdom. Festo has developed Bionic Handling Assistant, which is modeled on an elephant's trunk in terms of structure and overall function. The Bionic Handling Assistant works in an easy, freely moving and flexible way. It is safe, even if there is direct contact between man and machine. This is a sophisticated 3-segment bionic hand, which has gripper with the sensor. The adaptive gripper fingers enable fragile items to be handled without being destroyed. These hands can part of factories in future. Bionic Kangaroo. People at Festo has created this Bionic Kangaroo. This is a complex mechanism. It features pneumatic actuators that provide the jumping power and at the same time act as shock absorbers on landing. The necessary compressed air is supplied either from a small compressor or from a high-pressure storage device on board. Electric motors are used for maintaining balance and controlling the kangaroo's position with high accuracy, optimizing the tail and hip movements. All electric components rely on energy from rechargeable lithium polymer batteries. This 7 kg robot can jump 800 centimeters long and 400 centimeters high. The main focus of the Bionic Kangaroo project has been to learn how to create more energy-efficient and flexible systems that dynamically combine pneumatics and electrics and are capable of capturing, storing and reusing energy. The Dragonfly is quite the show-off when it comes to flying. It can hover in mid-air, maneuver in all directions, and glide without so much as a beat of its wings. Festo challenged themselves with the creation of a robotic addition to the Dragonfly family, the Bionic Opter. Each of its 4 wings has a carbon fiber frame covered by a polyester membrane and can be twisted up to 90 degrees from the horizontal. From tip to tail, the robot Dragonfly measures 44 centimeters long. Its sturdy and lightweight housing and mechanical system are fashioned from aluminum, polyamide, and terpolymer, contributing to its overall weight of just 175 grams. It is capable of maneuvering up and down, forward and backward, and to the side. By passing an electric current through the robot's 4 nitinol muscles, the head can be moved from side to side, while the tail can go up and down. Indoor or outdoor flight stability is ensured by the real-time automatic correction of in-flight vibrations. Bionic Ants. Festo is inspired not merely by the anatomy of ants, they are also inspired by cooperative behavior of ants. A large group of ants can work for a single task, so does Bionic Ants. The Bionic Ants work together under clear rules. They communicate with each other and coordinate their actions and movements among each other. The artificial ants thus demonstrate how autonomous individual components can solve a complex task together, working as an overall network system. In an abstract manner, this cooperative behavior provides interesting approaches for the factory of tomorrow. Future production systems will be founded on intelligent components, which adjust themselves flexibly to different production scenarios, and thus take on tasks from a higher control level. Bionic Swifts. Just see how gracefully Bionic Swifts imitate the real Swift. But Bionic Swift is flying without any camera. It is flying in a room that's had radio modules installed to serve as location anchors. Each of the birds has a radio marker that sends signals to the anchors, so that its exact position in the room can be tracked by a computer that acts as a navigation system for setting up pre-programmed routes. This makes it perfect for precision formation flying without crashing into each other or anything else in the room. If flight path be interrupted by wind or thermals, the birds are capable of making autonomous corrections, even if the path ahead is blocked by an obstacle. Festo's engineers have a practical real-world application in mind when developing the prototypes, and in this case the aim was to showcase a camera-free indoor 3D navigation system that could find use in the automated factory of the future. Bionic Wheelbot. The robot is based on the Moroccan flick-flack spider, which can walk like other spiders. It can also propel itself into the air. With a combined sequence of somersaulting and rolling on the ground, it is twice as fast in so-called rolling mode than when walking. The Bionic Wheelbot has 8 legs, enabling it to both walk and roll. They are controlled by a total of 15 small motors, which fit in the knee joints and body. There are also 14 automatic locking worm gear units that ensure that the spider only has to use energy when moving its legs, however, not to keep its body upright when standing still. In rolling mode, the Bionic Wheelbot does a somersault with its whole body. Just like the real flick-flack spider, the robot has an inertial sensor. Therefore, it always knows what position it is in and when it has to push off again. It is therefore much faster when rolling than walking and can even overcome inclines of up to 5. Bionic Aqua Penguins and Air Penguins. Festo has used the shape of the aquatic, flightless bird to construct 2 different types of bionic penguins. The aqua penguins use the bird's hydrodynamic body contours and wing propulsion to allow the robot to maneuver in cramped spaces, turn on the spot, and, unlike their real-life counterparts, swim backward. Aqua Penguin's wing skeleton is comprised of spring steel elements embedded in an elastic matrix of silicon. This lets the wings twist to an optimal angle with each stroke through the water. The pitch angle can also be regulated, giving the robotic penguins their maneuverability. The head, neck, and tail segments are based on a new 3D fin ray structure, derived from the anatomy of the fish's fin, which allows the penguin to change its organic shape to let it move in any direction. The bending structure consists of flexible longitudinal struts with circumferential connecting elements that maintain the shape of the elastic skin and help to steer the robotic penguin horizontally and vertically. The larger helium-filled air penguins use the same principles to lift the usually flightless bird into the air. To give the air penguin elevation, Festo designers filled a ballonet, or small balloon, with about 1 cubic meter of helium, which can lift about 1 kg. A system of carbon fiber rods and joints, moved by wires and pulley, are used to guide the penguins through the air. With the Aqua Penguins, a powerful electric motor, used to control the rate of flapping, and leverage system to regulate the amplitude of the flapping wings combine to almost perfectly imitate the kinematics of the penguin's underwater flight. The flapping cycles are virtually self-regulating, with little effort needed to maneuver the bird. The air penguins, on the other hand, rely on a series of mechanisms, called actuators, to control how often their wings flap and whether they move forwards or backward, up or down.